we're going to specify algorithms, and we're going to implement them. So we need some kind of a language to do that. So I'm going to introduce a very simple programming model, okay? Very simple kind of a language. It's kind of a pseudocode. It's actually the one that's used in this book. It's a very nice one. So understanding it, it's actually really useful, and understanding it will help you for many, many things. It's a really useful and good model for building concurrent and distributed systems, and it's much nicer than old-fashioned things like Java. You know, it's so old-fashioned, you can't do anything in Java. This model is much nicer than that. It's a kind of pseudocode. So the project in the course, which uses Erlang, Erlang is actually kind of close to this model. It's in some ways similar. So if you understand this model, Erlang will be very, very easy. Okay? So I want to talk about this model that we're going to use to write our algorithms, to write the code. So it's a very simple kind of a pseudocode, but it lets you write distributed systems. Okay? So we're going to write distributed algorithms. So the systems we built sort of look like this. You have these boxes here, computing nodes, computers. Here's two computers. And these dotted lines like a network connection. So there's some way to communicate. On each of the computers, we have some application. So here's an application code running on one, and the code of the application running on the other. So on the lowest level, we have network communication, okay? Channels, maybe TCP, UDP, whatever, some internet protocol, connecting these two. On the high level, we have the application, okay? So we're going to look at what's happening in the middle, the middleware. So what do we need here? Actually, we need stuff here to write algorithms, okay? And the stuff that we need is more than just TCP. We need stuff here that is stronger than the network protocols. So that's the point. So network protocols are not enough. So what does a network protocol give you? TCP, for example, gives you reliable stream communication for one-to-one between one node and another node. But what happens if you have groups? What happens if I have 10 nodes working together? Okay? One-to-many, one-to-one is not enough. Maybe you need more. So for example, here's some of the algorithms we're going to see in this course. So different kinds of broadcast: reliable broadcast, causal order broadcast, total order broadcast, terminating reliable broadcast. So these algorithms are like doing things in a group. So causal order broadcast means that if I send messages that are broadcast, and one message is causally before another one, that means they will always be received in that order. So Facebook, for example, it would be very nice to have this, causal order broadcast. TCP does not give you that, okay? Or reliable broadcast. What if nodes are crashing? What if they can crash? The naive broadcast, I send a message, I broadcast a message, and then my node crashes. Who receives? Well, if you don't use a reliable broadcast algorithm, you don't really know. Some nodes might receive, some might not receive. So it's very weak. Also, sometimes you need many-to-many. Sometimes you need to have a whole group of nodes doing something together. Like, remember, we actually talked about consensus, huh? They all have to agree. Or if they're doing a transaction, they have to agree. Or maybe you have like a group of nodes that are talking together, and no new nodes can join the group, and you have to do broadcast. But the nodes can fail too, they can crash. So somehow you have to manage this group, okay? So you have all these things that you need to do, and TCP is not giving you that, okay? TCP is giving you only reliable one-to-one, that's it. So we need more. So here's an example. So reliable broadcast. So what does it mean? Well, let's say I send a message to a group of nodes. But nodes can crash. Maybe the nodes receiving can crash. Maybe the sender can crash. So while the broadcast is running, nodes can crash. But I want the broadcast to be a reliable one. That means if one of the nodes receives the message, I want to guarantee that all of them have received it. All or none. So this is actually very strong. So let's say I'm broadcasting. Let's say I do naive algorithm. I send message to everybody one by one. And in the middle, I crash. So some of you have received and some of you have not received. This is not acceptable. This is not reliable. I want that if one of you receives, that it's guaranteed that all of the correct nodes, all of the nodes that have not crashed, receive. All or none. Either none, maybe I crash before I can send, then it's none. But if one of you receives it, all of you should receive. I want this guarantee. I want a strong guarantee, all or none. So this is important. If I receive a message, then I'm sure that everybody else received it too. So if there's like a conversation going on, or some collaborative work, I receive a message, I know that everybody else got it, and I can rely on that. Okay? So if like there's a collaborative editing or whatever, that's very important. Naive broadcast doesn't do it. Okay? So if I receive a message, but I don't know if the other guy received it, I don't know, maybe it's crashed, doesn't get it. That's worthless. That's a mess. I want simple, reliable broadcast. Okay. So this is called reliable broadcast. This is one of the first algorithms we're going to see. So how can you implement that? How do you do it? Oh, it's interesting. Huh? How can you make sure that you get this guarantee, even if nodes can crash? Well, it's actually not so hard. And it's one of the first algorithms explained in this book. Okay, another example, which we already talked about a little bit, is atomic commit. So you have a distributed database, like banks do, all of the banks do this, huh? They store all the transactions in a database. But what if the database crashes? What if there's a fire and it burns to the ground? Well, to take care of that, they have multiple copies, replicas, at different places, even very far apart, in different buildings, in different cities. They have to be far, because they don't want, if they're both of them sitting in the same building, building burns down, they both burn down. So they have to be far apart, okay, for reliability. But then you have this interesting question. If you do a transaction, you move money from one account to the other, both of the databases must have the same decision. They must guarantee, even if a crash can happen anytime, anybody can crash during the execution, but they still, you have to guarantee that. That's a very strong thing, huh? That's a strong property, okay? So we need to do that. So we're going to do that. That's one of the things we're going to do in this course. You're going to see that all the companies doing critical stuff, mission critical, like banks, they all do this, okay? So these algorithms are like real practical, hard algorithms. They're solving hard problems, huh? They're real stuff, okay? So this is the kind of stuff we want to write. And now I'm going to show you the code, how we write it. It's called event-based component model. So actually, it's the code we're going to write is going to follow the model we saw before. So each node is going to be a program running, okay? And there's a clock ticking, a global clock. So in the model, it's like time-space, huh? Every node each node does something and then somebody does something. And each tick, one node will either do a computation step or a communication step. We saw it already, yeah? So there's actually different models. What we saw was this one, the model of Etienne Welch, where you read all the messages from the inbox and you send at most one message to each neighbor in the outbox. Okay? So that model, we defined it precisely. But there's other models too. So I mentioned them because the code we're going to write, it works for all the models. Okay? It's actually very simple. So Gary model is receiving one message and sending one message, or you can at most receive one and send at most one. So there's modeled by Nancy Lynch in the Nancy Lynch's book. So there's different variations. Okay? So we saw this one with the in buffs and the out buffs. But the others actually, they're all kind of similar. So we have to see one, so you understand it. But actually others are not so. And the programming we're going to do works for all of the models. Okay? So it's not limited to this Atiyah and Welch. So each node will execute a program. And each program has these yellow boxes, which are called components. Okay? And these components, you'll see they're kind of like a stack. And each component, so at the lowest level, we have these yellow boxes. And the yellow boxes will receive events. You'll see what it means. I just follow. So each box, it waits for something. Maybe it receives a message. It does some local computation. It has local variables. And then it sends a message. Okay, trigger means send. Upon event kind of means receive. If you don't like the terminology, you can send hate mail to these guys because they are the ones, but it's actually very logical, even though it's a little bit strange in the beginning. So upon event is like a receive. I'm waiting for something, and when it happens, like a message comes in, I do some local computation, and it's single thread, so just some instructions here with local variables, and then I send a message. So send trigger is like a send. Okay, so that's one component. So what are these events? So messages, I can receive messages. Also there's timers. Maybe the local node waits for a certain time, or it also can wait for a Boolean condition to be true. For example, I have a set, it waits until the set is not empty, and some other component will fill the set. And messages can flow down, up, or up. But let me show you the picture of a multiple. So this is how one node looks. Okay? So remember I showed you this picture with the network channel on the bottom and the application on the top and the middleware. Okay? Each of these yellow boxes here is like a component. So here's database. So this is inside part of the application here, some database. It sends a message down. It needs to do commit. Okay? So it sends a message down. Messages going down are called requests. So this commit will receive the message, it will do some computation, and it returns the result. Result is called an indication. Okay? So requests are messages going down, and indications are messages going up. Don't shoot me if you don't like those words. Shoot these guys, because this is the terminology used in this book. Okay, it's actually not too bad once you get used to it. So so there's like a stack of components. On the bottom, you have network components. So here, this is a perfect link. So this will do like TCP. It'll send messages between one node to another. So the database needs to do a commit, but the commit component by itself, it might need to do reliable broadcast. So the commit component sends a message to reliable broadcast component. But reliable broadcast needs to send messages on a network. So it sends message requests down to perfect link. And if the message comes in over the network, it comes up. Okay? So there's also a consensus component. So the commit component will need to do consensus. So the commit component can send message down to the consensus, and it gets a reply back up. So it's like a software stack. Huh? Each of these yellow boxes is a sequential program. It's like sequential. It's like single thread. So this whole thing is like concurrent. Huh? I can have a message going down here, and this one will receive the message, starts doing stuff. Maybe it sends another message down. Maybe it sends a message down here. maybe this one needs to send a message down here. Eventually the messages come back up, the results come back up, the result comes up. Okay? So it's like a stack. So we're going to build code like a stack. Okay? So it sort of looks like that. Now, something special that I have to mention to you. If I have these two yellow components here, I make them yellow. Let me find some yellow chalk. Some yellow. So these are these yellow components here. These yellow ones. So messages going down are called requests. Okay? Messages coming up are called indication. So the application maybe does a request, it does like that. But inside the component, I'm sending a message. But maybe I send a message down, and here I'm receiving a message. Okay? But the indication, I send it here, and I receive it higher. So you see why you need different words. Huh? I send a message, and I receive a message. But if it's going down, it's not the same as if it's going up. I have to make a difference. Because the messages going down are like from higher components to lower components. And the messages going up are like results coming back. But this message going down is a send, and it's a receive. The message going up is also send and receive. Okay? So that's why that there's two terminology. There's send and receive, and then there's request indication. So a request is a message going down. But when I do send, I don't know what the direction is. Huh? I do send. But maybe the send is going received down, or maybe it's received up. So if it's received down, it's actually a request. If it's received up, the message is an indication, which is like a result, a response. Huh? Indication is like a response. I don't know why they call it indication, because response would have been a better word, okay? So maybe I should ask Luis or Rashid the next time I see these guys. For some reason, maybe it's because English is not their native language, I don't know, okay? But that's the words that they use. But it's actually nice to have words that are kind of unique. So a send instruction, again, there's slightly different terminology. The send instruction in the code is called a trigger, and the receive is called upon event. Okay? So these funny words. So I have to use these words because the book uses these words, and it's a good book. So trigger, and this is like a record. Huh? This is send bcast is like the label or the type of the record, and then you have some arguments. And upon event is like a receive. Huh? So del bcast is like the type of the record, and here you have like arguments. So basically you send and receive messages which have data in them that are kind of like records. Okay? So the send instruction is called a trigger, and the receive instruction is called upon event. And the send can be both a request or an indication. Request if it's going down, indication if it's going up. Okay? And the receive can receive a request or receive an indication. Okay? So this diagram here, or that slide, basically explains the whole notation, the whole kind of words we're going to use. So applications, distributed applications, will sort of look like this. So here we have 3 nodes, P1, P2, P3. Each node has this software stack. Yeah? Application, channel, and the application on the top, the network communication channel on the bottom, and then some distributed algorithm in the middle. So here's a broadcast. So for example, here this app code does a broadcast. So it sends the message send broadcast to bcast, which is the broadcast. This one will send 2 messages, one to P2, one to P3. The P2 message arrives here, and basically it becomes a deliver message, comes back to the broadcast, and actually it delivers a deliver message, the result back to app on P2. And the send P3 will go to here. This is turning into a deliver P1. So P1 is the source node here. And bcast will get this deliver message and send a deliver broadcast message to the app. So you see, each of the components is like doing local stuff. It's getting requests. It's sending requests. It's also getting indications. And it's also sending indications. Okay? So programs are sort of looking like this. And each of these yellow boxes is like one thread. So completely concurrent thing. Each of these boxes is like always waiting for messages to come in from either this way or from this way. So the bcast either can receive a request from higher, or it can receive indication from below. So there's two kinds of things that can come into this bcast box. See how it works? So this is the notation we're going to use through the whole course. And it's actually really nice, and it's good to know it forever. If you look at distributed algorithms, any kind of a complicated distributed system, this notation is very nice for doing it, for explaining, showing the code, understanding what it does. Okay? So all of the algorithms, so we write, they're going to be like this. So we're going to write the code that's inside the yellow boxes in our algorithms. Okay? So algorithms will be just little bits of pseudocode inside of those yellow boxes. Okay? Reasonable? But it'll become all very clear when we start writing code. I'm going to start writing code, and then you'll see how it works. Is that okay? Any questions now? Yeah?
I'm sorry, it is still the component 1? It's like at page 7 you said it's one of the components, and I just want to check.
Yeah, these yellow boxes, so a component can receive things. So messages can come in there. These yellow boxes, messages can come in, and then you have inside, you have a piece of code waiting. I'm not sure if I understand the question. So this one will take the message when it comes in, it runs the code, and then it can send a message. So trigger is a sender. It sends back out. So maybe it receives a message coming in, and then it will send a result back. Okay? But the send and the receive can go different directions. So the trigger, the send here, maybe it's sending down, or maybe it's sending up. We don't know. It depends on how the boxes are connected. So this trigger, it could be either a request or indication. Because it may be the send is sending message down, or maybe it's sending message up. We don't know yet here. Depends on the boxes are connected.
So it's not the same thing with page 11?
Yeah, it is. This yellow box is the same box as the yellow boxes on page 11. So these yellow boxes are the yellow boxes I just showed you. So a yellow box can receive messages from other yellow boxes. Maybe it's coming from higher, or maybe it's coming from lower. And when it receives, it does upon event. So you have the code inside here. And the yellow box can send messages down to other yellow boxes, or maybe it sends the message up. So here bcast is sending message down to channel, but this bcast is sending message up to app. Okay? But both of those are sends. So this is send going down, here's a send going up. So the send going down is called request, and the send going up is called indication. Okay? So I say it many times, so but it's very simple. You just have to realize that send receive is not the same as request indication. Send receive is just a send, is messages going and being received, whereas request indication gives you the direction, going down or up. Okay? The request is a send receive that goes down, and indication is send receive that's going up. Okay? It's okay for now. We're going to see code with this. Lot of code with this in this course. So this is a really nice way of doing algorithms, as you will see. Very complicated algorithms can be written in a very simple way, in this notation. This is a concurrent distributed system. Remember that distributed systems are very complicated things. It's probably the most complicated code that you're going to see in your life. Okay, complicated in terms of conceptual, complicated. It's very. You'll see we're going to see very complex algorithms, but in this notation we can see them in a very simple way. So hopefully, even though it's complicated, it'll be kind of easy to understand. I hope. We'll see. Okay? So that's it for the notation, for the implementation. So this is how we're going to write our code. So this is implementation.